Well, welcome back, everyone. Looks like we can get going. So for today's class, we're going to be doing, as the Moodle website seems to indicate, loads and loads of linearizations. Turns out if you linearize a function enough times, it could be considered Newton's method, and it's a great way to solve equations. So we're going to solve some of the weirdest equations ever that you might try to approximate solutions to, purely just by linearizing the unknown function or the given function of these problems. So this is going to be kind of an interesting exercise set. This one's going to be highly, highly calculator intensive. And so for these problems, it's more just a great application of using the derivative, but they're not necessarily going to make really good exam problems, I'd say. So this is just a interesting kind of section in that sense. But before we get started, are there any questions that folks would like to begin with? Okay, well, with what we've got going on the schedule so far, our third exam is going to be next week from today, so we'll have that done before the Thanksgiving break that's coming up. And it only goes through these sections here, up to section 4.7. And that means there's a lot of applications potentially on this exam, but I can't ask a question from every single one of these sections necessarily, or else the exam could be too long. So essentially, this is what I'm going to do. These two sections here at the start are both application sections. This one's exponential growth decay. This one is related rates. And over here, this one's optimization. So we have three potential questions on the exam. But what I'm going to do is I'm going to use a random number generator to pick two of those three. So those will be the actual official exam 3 questions that you'll see on the exam. So it won't be every section. I'm going to pick two completely at random. Any questions about that so far? Okay, well, let's go to section 4.8 then to see how all this information goes. Then section 4.9 is going to be about antiderivatives. And finally, in chapter 5, we'll be looking at integration. So the second process or big process for our goal in this course. So here's how the notes start. They say, estimate the real roots of this equation. We say real roots here only to emphasize we're not looking for the complex valued solutions to this, just the real valued ones. But we're going to try to solve this equation by linearizing a suitable function. Honestly, for these problems, sometimes that's the most confusing part right here. It looks like we have two functions we're dealing with when we solve this equation, but there's only one function we're going to be linearizing. And here's how it goes. If we were going to try to solve this equation, we would probably try to employ some kind of factorization if we could. That's the biggest tool we have. And to make that work, we would want 0 on one side. So we're going to start by copying that approach. Add 3x to both sides, and you get a new equation. Slightly more friendly, it's x cubed plus 3x plus 1 equals 0. The moment we have that, this is the so-called suitable function that we were looking for. And this is the main strategy on all these problems in this section at 4.8. Get 0 on one side, then try to solve this equation. And looking at it, it looks really terrible. I could factor x out of the first two terms, but that's not a factoring of everything, so that doesn't even give me a solution from that little bit of factoring. There is a degree 3 formula for these polynomials, but that approach fails as soon as you make it power 5. There's no formula for that, so we should see how to solve this one, since it will apply to any polynomial equation. Let's now start by saying let f of x be equal to x cubed plus 3x plus 1. Yellow to just emphasize that's the suitable function we were looking at. And the moment we have a function like this, we should use extra tools. Even on the homework, this is why these make kind of bad exam questions in all honesty. We should get the lay of the land and see what this about looks like. So I'll put in f of x equals x cubed plus 3x plus 1. And it says estimate the real roots. This is what we're looking for right here, negative 0.322. But we want more accuracy than that in this section. We want at least 6 decimal places of accuracy. Desmos, I don't even know how to make it give it to us. We're going to do that using Newton's method. First thing we want to do is make a guess. Let's take a look here. It's about negative 3.22. Let's guess negative 0.5. And note, that is way off, right? It's definitely not negative 0.5. That's way down here, not hitting 0 at all. But nonetheless, let's make that our guess. So I'll put down here just for a quick graphic to show where that came from. Oh, didn't want that there actually. Let's use this value and say linearize. There's some weird problems with my Word document. Probably should have done that with that thing. Let's see if it stabilizes. There it goes. Linearize f of x at the yes a equals negative 0.5. So what I mean by that is you could have used the value that was right here by the red dot, but you just need some number to linearize the function at, and I'm going to use it at the negative 0.5 here. So now we just want to linearize that whole function. We'll graph it and see what it looks like together, the function f itself and its linearization. So linearization is a step all in it, is a process all in and of its own. It'll go first. We have a function value at a, so let's calculate f at a. This will be f at negative 0.5. So back to the function f, we're plugging it right up in here, negative 0.5 cubed plus 3 times negative 0.5 plus 1. Let's throw that all in and get a value out. So there's, again, a couple ways to do this in Desmos. If you go f negative 0.5, it just spills the beans, negative 0.625. But if you typed it in, like, say, an ordinary calculator, let's put it into the TID3. Here's what it would look like. Again, another reason why this is not a great exam question. TID3 works pretty good for these problems. So does the TI-30X2S if you have that calculator. So let's put in negative 0.5 power 30 plus 3 times negative 0.5 plus 1. And looks like we got the same value at negative 0.625. So we're linearizing the function. A is negative 0.5, f of a is negative 0.625. Next thing we need to do is we need to calculate the first derivative and evaluate it at the same a value, negative 0.5. So back up here, let's calculate f prime of x. This will be a 3x squared plus 3. The constant 1 goes away. And so now we'll calculate f prime at negative 0.5. Let me write out this way just to connect the dots as we've been doing on the last section. A is negative 0.5. I'll write in at this step. So 3, negative 0.5 squared plus 3. Back to the calculator. 3, negative 0.5 squared. Okay, I think we've got it in, plus 3. And now the value is a 3.75. So we can now take these two ingredients, throw it in inside the linearization, and we'll have linearized that function. So the linearization by formula goes L of x equals f of a plus the derivative of f at a, so f prime at a. It multiplies x minus a. So dropping in all the information, we finally have that the linearization at x equals, first for f of a, it's the value negative 0.625. Then from plus to plus, the derivative of f at a, we found a value 3.75. And last, it's going to be x. It's minus a, but that's minus a negative 0.5. So I'll just write it as plus 0.5. So that's the situation so far. We took a pretty complicated polynomial function, complicated in the sense I don't have a clue how to factor this thing, and I still don't, and we linearized it. This is a really big punchline in just calculus, whether you're in calculus 1 or calc 3 with multiple variables. Sometimes these problems are so hard, even this a polynomial equation, that if it's too tough and we need approximate solutions, just linearize it. Let's show what that has done for us because it's not completely clear how this helps solve the equation. But in Desmos, it becomes more clear. This is the curve in red. That's a complicated curve. Now let's throw in the linearization. L at x is negative 0.625. This is also a test to see if we even linearized it correctly. Plus 3.75, x plus 0.5. And yeah, that looks like a great linearization. The red line and the green and the blue line, forgot my colors there, they look completely the same right next to that point of intersection, the negative 0.5, negative 0.625. So we've got a great linearization. But also, recall we were trying to solve this equation, which now has a 0 on the right. The red dot goes through 0, and a spot here that's kind of hard to solve. But the green line, that's a linear equation. This is really easy to solve this one if you set it to 0, and tremendously hard to solve that one. So now that we have a linearization, also note they agree very, very closely when you set these equal to 0 and solve. So let's see what we get from this right here. Let's set this to 0. So now that's a pretty nice equation. I'll leave the 3.75 here. Let's just add 6.25 to both sides and then divide by 3.75. We get x plus 0.5 equals, first add 0.625, here it is. My next step is to immediately divide by 3.75. We can subtract the 0.5 on the next step. So now next step, x equals 0.625. Actually, I want to write this slightly different. Minus 0.5, there we go. Plus 0.625 division by 3.75. So now we just about have a value out. Negative 0.5 plus 0.625 divide by 3.75 gives us this value right here. This is our approximate solution. Let me check that graph again on Desmos. So the blue line, oh yeah, I must have got the numbers backwards when I was looking at it. We have agreement and we have more accuracy than Desmos provides. Looks like it's literally a third on here. So I'll say equals negative a third. Now that's not the exact 0 to this function. When we look at Desmos, we know it's off by a little bit. Looks like it's negative 3.2 repeating potentially. So whatever that number is. And it might not be repeating. I can't even tell through Desmos. But that's pretty close. And here's how Newton's method works. Newton observed that you could just do this again. You could take this. That could be your initial guess. Relinearize the entire function based off that guess. And solve the new equation right here. That's a lot of work, right? But Newton also knew that you could just take the original linearization equation, this one. If you solve that set equal to 0, you obtain a recursive formula that you could just keep on hitting enter on a calculator, a nice enough calculator, or even in Desmos, and get successive approximations. You're essentially linearizing every single time you hit enter. So here's what Newton did. He took this, he's going to set that one to 0 and solve the linearization equation. And here's how it looks. L of x, now set to 0, would mean the linearization of x goes f of a plus f prime at a times x minus a, now set to 0. And we can solve that essentially the same kind of way. First thing we're going to do is subtract f of a, then I'll divide by f prime of a. So it'll just be an x minus a. We can, in fact, drop the parentheses at that step. So subtract this f of a to start. So here's minus f of a. Divide by the derivative, f prime of a. It would go right here. Already we can note that this process will not work if the derivative of f at a is ever 0. You would have divide by 0 right here. So as a process, it can fail. It just depends on the geometry of the problem and where your initial guess is. You have to prevent 0 in that location. Next, just like we did before, I'll add the a, which is like subtracting the 0.5, and we get x equals A minus f of A divide by f prime of A. The value here is just the initial guess. And sometimes instead of calling it initial guess, we call it x naught, the first value of x that you're putting into this process. So x naught is the initial guess. The value here we might call x1. It's the value you get after running this through the linearization and solving it for 0. You might automatically get x1. So this is the next approximate solution. But then what we want to do is, once we have that next approximate solution x, feed it back to Newton's method and get a better successive approximation. It becomes a recursive formula. And here's what it turns into all together. First, we make a guess. That's going to be our x naught value. Then you use that first approximation to get a second, a third, and a fourth guess. It combines in this format. So the nth approximation minus f at the nth approximation divided by the derivative of f at the nth approximation is the n plus 1th approximation. It's kind of hard to say, but all it is linearization done potentially dozens of times. You'll have your f of xn here, your f prime of xn here, with a warning, your denominator could never be 0 on any one of these successive approximations. And a lot of the problems in the book are going to ask us to be accurate to either 6 decimal places or maybe 8 decimal places. And here's our author's rule of thumb. You'll have an answer that's accurate to, say, 8 decimal places if your nth approximation and your very next one agree to those same 8 decimal places. So we'll go by that as a rule of thumb. So that's the whole process. Really, it's just right here. This is linearization over and over and over again, the same exact linearization like we saw in section 3 point, I believe that was 10, a while ago already. Well, let's try this out on a brand new problem. This one right here, cosine 3x equals x. Or folks would like, we could try it out on this one and see just how accurate we could get. I'll leave it up to everyone in the class. Should we try Newton's method on this one here? Or do you want to try it on a new problem down below? First one, good call. Let's give that a try and see what we get on this thing. So for the first one, what we need here is an initial guess. We have it. We need the function and we need the derivative. So let me just copy this much right here. Oh, geez. Sorry. Kind of debating myself on where to copy from. That should do the job. So now we're going to give this a real try. I'll put it right here. No, probably better right there, right in front of Newton's method, so we see what we're looking at. I will do example 2 right after. Okay, so here's how the process is going to go. The very first thing I would want to do if I'm using Newton's method is get the guess, get the function value at the guess, get the derivative at that guess, and then just copy down this recursive equation. It is xn plus 1, the next guess, is the prior value xn plus the function at that prior value. So f of xn divide by the derivative of f at xn. And here, let me just put it here for easier reference. X naught is what we're going to call our first guess, set to negative 0.5. It's now playing the role of A, and I only copied that since we're just used to seeing it when we were doing linearization back in the day. Feels like a long time ago already. So let's try to get an answer to that equation accurate to, say, 6 decimal places. In a TI-83 or even the TI-32X2S, these are really great calculators for recursive formulas. And here's how it's going to go. The very first thing you put in is whatever your initial guess is. Just go negative 0.5, enter, and it's done. See if I can turn up the brightness on this thing. After we have that out, here's the tough part. We need to put this into the calculator. Oh, but I forgot we also have to expand it out. So let's write out what f of xn and f prime at xn is, so we know what it looks like. Xn plus 1 equals xn now, plus, in the numerator, we're going to the f of x, it's right here, replace all the x's with xn. It'll be xn cubed plus 3xn plus 1. I think I got a little over carried away with that fraction bar. Now for f prime at xn, here's our derivative right here. It'll be 3xn squared. Maybe move that little tab out of the way first. Plus 3. So in its expanded form, that's what's actually going in the calculator. So I wrote down the formula, forgot to expand it, but at least we got the initial guess in. So now back to the drawing board. Here's how all this goes in. Put in your initial guess first. So there's the negative 0.5. Now we have to copy in this into the calculator, and here's how it goes. In place of xn, we want to use prior answer, negative 0.5. Oh, something weird happening?
I see what you're doing there. I don't.
Oh, gotcha. Yeah, we're going to go second answer. Is that what you were saying there?
Yeah.
Yeah, this is what's allowing weird formulas like this, even if it's recursive, to really work in the calculator. So here's our answer. And oh, hang on. I missed one big thing. There's a minus right there. Darn it. That's a bad thing to miss. Let me kind of indicate where that is. Minus should have been here and here. Let me fix those two really quick for us. You notice that your work isn't just not coming to the right values. It could be something silly like that. Definitely have to carry in the minus sign. Now I have the answer. Here's the minus. Now we need a parenthesis for the entire numerator here to start off. Go second, the answer key to refer to xn, power 3 cubes it, plus 3, prior answer, plus 1. That takes care of the numerator. Now go division, throw in the denominator. It'll be 3, second and a negative sign for prior answer, but it's also squared, plus 3. And if I make any mistake here, if I like flip a sign like this one here, like we just barely caught, or even if it's small, if I put in plus 2, there's a high chance this is not going to work out, not even a little bit. Your numbers might get bigger and bigger and bigger until your calculator just says out of domain, or they could start oscillating, positive, negative, forever. That's when you know it's not working. There's some instability. This should actually work pretty fast for us. So if we hit enter once, that's the first value we got. We made an initial guess of negative 0.5. We linearized, we solved the linearization equation, and we got negative 1/3. Then we mentioned Newton did this. Take negative 1/3, plug it back at the top and run the whole process. But in the calculator, Newton didn't have this luxury. You can just press enter. There's the next refined answer. We're going to keep on hitting this until it agrees to 6 decimal places, or the whole line agrees. That's not a bad thing to do. It already changed a little bit, but there's stability on the first 3 terms already. And maybe the first 4 terms, or maybe just about all of them. At this stage, there's no change. We've linearized several times, and we got so close that this line that you see right here, the blue line, the linearization, it's essentially over here now. And we're really approximating that solution to high accuracy all of a sudden. And that's wild because, again, that is not a nice equation. I still don't have a clue how in the world I would solve this thing, but that's okay. Linearize enough and you have a great solution. We'll say down here, x is approximately, we're going for 6 digits of accuracy, negative 0.322185. Have you noticed that some of the rounding kind of seems odd in the back of the book? The instructions are asking for answers that are accurate to 6 decimal places. So that means he's going to round by truncation and only pick off these digits. Oh, I forgot. forget where to stop right there. So even if the value to the right over here was like a 7 or something, and it would have rounded up, they're probably just going to go like this and give the answer accurate to that amount of digits without actually changing anything. Again, just rounding by truncation at that point. I'm not picky about that. So if you did round up, I don't worry too much about that. Well, any questions at all, folks, on getting through this problem here? Yeah. It's the trick with the prior answer. Every time I hit enter, let me hit second enter a couple times. Well, I hit it once. Every time I hit enter, it's using this whole equation. And when it refers to A and S, it's just using the very last line.
Oh, so it's not the answer from the line above, it's the answer.
Exactly. Every time I hit enter, it puts the new value, say this number right here, back into that entire equation and recalculates it on every single stroke of enter, which means every time you hit enter, you're actually doing this. You're relinearizing and then solving it all in one go. Just a huge amount of mathematics in one step. Does that make sense at the moment? Cool. No, you don't have to show those. Yeah, pretty much what you'd write on paper is just about what I got right here. You want to find a function by setting one side to 0, then find a guess. We don't actually need any of this. Let me just strike it through because I took a screenshot. And in my screenshot, let me take this rather. What I would need is just this and this in the homework. Sorry, this is a problem that was bigger, and so it doesn't have as many steps as you need. So here, 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 then write out this and your end value, and that's pretty much the end of the problem. So actually, they're pretty quick problems to get through. Other questions at the moment? Yeah. Well, for rounding to 6 decimal places, we just needed the first 6 digits to stay the same.
What, 5 times?
Something like 5 times up there. Yeah. What's that? It's going to depend on the problem. Some problems you hit enter twice and it's giving you the same value back. On the different problem, it could take like 50 times. I think that's a little bit rare. But if your derivative is close to 0, it could take 50 times, thousands of times. It could take a while to get to the actual solution. If that ever happens, we would just take a different initial guess. Maybe negative 0.25 is too far away. We need to move closer, something along those lines. But for most of these problems, just a few clicks should get you right where you need to be. Other questions so far about that? Okay. Well, how about we try out an even worse equation then? This next equation is absolutely terrible. If I try to solve this, I would try to take cosine inverse of the left side. That would free up 3x, but now you have cosine inverse of x on the right-hand side. You're always trapping an x variable no matter what you do. This one's just as bad. To solve this for x, you might try the natural log, because then you can get x to come down from the exponent position. But now all of this is trapped in the natural log, and you have an even worse problem. So these are just some really strange equations. I don't have a toolkit for solving these, except for approximately. So we're going to do the same exact kind of process. We want our answers accurate to 6 decimal places. And the very first thing I would do on this problem, like immediately, it's a technology kind of problem where you really should plot it to get a feel for what is even a good initial guess on this thing. I don't necessarily have any clue. And I might be jumping the gun on this. I don't even have anything to plot. There's still one thing I need to do first, right? We need to find a suitable function that needs to be used in Newton's method, which essentially just boils down to get 0 on one side. Let's write that as our step 1. Get 0 on one side. That means there's really 2 ways to do this problem. Some people might subtract cosine 3x. Some people might subtract x. But your solutions will agree. So all roads lead to Rome on this. I would probably just subtract x to get this one started. So you have cosine of 3x minus x equals 0. That's still highlight worthy because that's how the procedure starts. Next, we can define our function by saying let f of x. Let me maintain the same color coding from before. So green for f of x be equal to cosine 3x minus x. So f is now the right-hand side. Now is a good time to plot it. I think I jumped the gun a little bit on that. Let's plot f of x is cosine 3x minus x. And my scale is definitely not good. Let's fix this. It's out there somewhere. Here it is. Let's maybe blow this up. This is a lot going on. So it's a trig function, so we should expect an oscillation, but also negative x is tied in with it. So we have negative x and cosine oscillating at the same time. But we're trying to find where this crosses the x-axis. There's one right here, but there's two more right here. This problem is a little bit tricky, and this happens on the homework too. We have to hunt for all the solutions on this thing. That means we have 3 initial guesses trying to get to these 3 different zeros here, here, and the one over here. So let me try to find a window to just put this in. That ought to be a good enough screen. This does not have to go into your notes, but it's really just here for the sake of emphasizing how we're going to pick our values out. That's way too small. Let me go like that. So we're going to have 3 initial guesses, and we'll say let x naught, our initial guess, be equal to, we need a value out here to try to target the 0 in this location. And if we zoom in a bit more, you might pick something like -1. That ought to work. Probably -2 might even work. These things are actually pretty forgiving. But if you pick -1, you might not have to click the enter key on your calculator 30 times if you pick something far, far away. So I'll start with a -1 on this one. Then over here, I need a value. I'll just pick a -0.8. So I'm sure that ought to linearize nicely for us. Then down over here, let's pick, say, 0.4. These were just my picks. When you do this on homework, some people might have picked, say, -0.8 to try to target this one. You might have picked -0.6 to target that 0 there. Some people might have picked +1 to go for this 0.4. As long as the numbers stabilize and you get an answer that's close to where you expect, all those methods are going to be just fine on these problems. So we have a function. From the function, we know what the initial guesses ought to be. Next thing we ought to do is take the derivative of that function and put it together in Newton's method. Any questions at the moment? Okay, so let's take the derivative of f. I'll put it up here. F prime of x. First, we need to navigate through a chain rule. The derivative of cosine is going to be negative sine. Input that goes inside is going to be 3x on both. The derivative of that negative x, clear over here, just becomes a -1. So f prime of x is now equal to, back over here, we have a derivative of 3 by that 3x prime. So I'll write this as -3 sine 3x minus 1. So with the function, its derivative, we can now assemble Newton's method. Which will go like this. The next approximation, xn plus 1, is the prior one, and don't do as I did earlier. Let's keep this as a definite negative sign in that location. We'll put in the original function in the numerator, the derivative of that function in the denominator. Next step, let's just fill in what we have right here and show that Newton's method should be like this. Xn plus 1 equals xn minus, for f of x, we'll put in cosine 3x minus x. And in our denominator, that looks kind of weird for a fraction bar. Let me fix that. For our denominator, just put in -3 sine 3x minus 1. And I did practice this problem this morning, since these are problems that you don't want to screw up on the calculator in front of everybody in class. That's not a great use of time. But when I practiced this morning, it took me a lot of tries to get this one right. I messed it up putting in the calculator first. I corrected that. And then I spent another 10 minutes this morning just messing it up repeatedly. This is what I messed up in my calculator. It's a trig function, so the first thing you should check, even in the TI-32X2S, is the mode must be radians. If it's set to degree, we're not going to get the right thing at all. It's never going to stabilize. Our answers are just going to look really, really weird. So make sure you're in radian modes anytime a trig function comes up, and you know you're going to operate the calculator to get through it. Okay, with that out of the way, let's give this a try. Again, this is a tricky problem because we're going for 3 different solutions. I'll record them down below here as we find them. And so we need to go off of 3 different initial guesses. So let's start off with our -1. Once -1 is inserted, we're just putting in the right-hand side of this equation. So second answer refers to that -1 minus, and then parenthesis for numerator for sure. Here we've already got the minus, we just need cosine. 3 times the answer, prior answer, then minus that prior answer. So that's our first line right here. And this calculator is actually kind of convenient in a way because it wraps around. You can see everything in one screen, usually. Then division by this stuff. We have to lead with this negative sign specifically. So -3 sine 3 times a prior answer. Close that parenthesis and -1. And close that final parenthesis there. Now, even the parentheses are important. If I went like this, 3nths -1, then I could guarantee you I'm never going to find that mistake. That's a really hard one for me to find personally, especially if I made it. Now it's my error. And this is never going to work out. But you know what? It's kind of interesting to see what happens in the calculator when something goes a little bit awry. So let's stick with this and see what happens. I enter on this, and we get -0.995. And you know, that looks plausible. It looks like it's improving. And if we keep on hitting enter, my values, they just keep changing on me. Now I'm at -9.7. It looks like it's stabilizing though, but you notice it's a lot of enters out of nowhere. This would be unusual. And no matter what I do, I get -0.979. Let's check the Desmos graph on that. -0.979, you know what? It's actually potentially working. That is really weird. Usually it's really completely blows up when you make one of the simplest mistakes, but this one might actually be working out, as strange as that seems. Well, let's fix this and see if we can get to that same number as before. I'm curious now. Let's record these results temporarily. Let's fix our mistake and see what happens. That might have been a mathematical miracle of some kind, but let's try this out again. I'll start with a -1. -1. I don't necessarily want to type this out again, so hit second, enter to refer to prior entry. Do it again. And there's our prior entry. So that saves loads and loads of time. I'm going to left arrow, I go 3, answer, close the parenthesis, then -1. Then close that parenthesis. Let's see what happens to the stability of these numbers. Starts at -0.982. It linearized again, -0.979. And after a while, I just start jamming the enter key until it stabilizes. Notice how fast that happened. It's done at this stage. Really, the whole screen matches the numbers. And how close were we? -0.979, 366, 8032. I wonder if that would even make it to where it was needed to go, but we got to where we need to be much, much faster regardless. So I believe that that's the more accurate answer. If you really want to test this out, take that digit, plug it into the original equation, and just see how close it is to actually balancing, or the equation here. But that's our first value to 6 decimal places, 9.979366. That feels weird to me because I'm always tempted to round up on these, but that's what they're going for these problems. That's accurate to 6 decimal places now. So that's one down. We have 2 more values to find, but it's just a matter of just changing your initial guess. Any questions at all, folks, so far on that first value? Okay, then like we mentioned, if there's multiple solutions, which does happen on this homework, you don't want to hit and clear all this out. Just type in negative 0.8. So there's our new initial guess at negative 0.8. So we're in this region now, so we're targeting that 0. Hit second, enter, do it again, second, enter, until that comes up. Then here's our first iteration, second one. It's changing a lot on the third, fourth. Right around now, it's stabilizing. And at this stage, I hit enter quite a few times. You don't have to track how many times you've read through the iterations. It's just sometimes interesting. After about 5 or 6 iterations, our answer is highly, highly accurate. But it's always a good idea to double check these. I would always go back to Desmos to see if I match at least with the digits they gave us. Negative 0.8877. That's really good numerical evidence. We probably have the right answer. So negative 0.887726. Then one more to go. It's pretty much rinse and repeat at this point. I'll plug in 0.4. Second enter again. Then a bunch of enters as necessary. And notice how fast this one went. In 4 iterations, it's repeating. That's because we picked a value that was just excessively close to the real solution. That's a good strategy always to try to take on these problems. So it's 0.390040. So that's all 3 solutions to this really, really strange equation up above right here. So again, the whole purpose of this section is just an application to calculus. If you like this kind of work, there is an entire course at ISU called numerical analysis, where they look into taking ordinary problems like solving equations and see how to make the machine do it. This is a routine that's programmed into calculators with lots of refinements, tons of refinements, but your calculator, when it solves an equation, is using one of these basic routines like Newton's method. Well, any questions at all, folks, on getting that? Yeah. Yes, absolutely. Let's give this a try. So I'm going to try the 0.4 again to start. So I go 0.4 and then enter. Once we're at this screen, let's go second and negative sign. I'll just refer to it as A and S for prior answer. So we need a minus here. And this is where it always gets sketchy in putting this in the calculator. We need to be very careful with parentheses for numerator, denominator. Sorry, say again. Alpha y equals. I've never tried that trick. What does alpha y equals do? Sorry. Oh, gotcha. Yeah, I don't know if my calculator supports that on this one. But let me try are you using a TID4? Let me try it over here, see what it does. So on this calculator, let's start, well, I turned it off. There we go, 0.4 to start. Then second minus, another minus. And you said it's alpha? This up top?
Yeah.
Gotcha. Oh, that is really cool. I've never seen this before. So the first option right here. Hey, yeah, that would work a lot. So that organizes it a little bit better on this calculator for sure. Then cosine, 3 prior answer. We have to remember that trick. Thanks for mentioning it. Minus the prior answer. Then I guess down arrow to get to your denominator. Then minus 3 sine Oh, almost made a mistake. 3 times the prior answer again. Only trouble is those are tinier pixels, I guess, but if it's right in front of you, that's not an issue. -1. And I think that should be it. Does that look right to folks for that entry? Awesome. Hit enter here. There's the 0.390084.
I had it on float 3, that's fine.
Oh, gotcha. Hit enter one more time. Oh, it's just showing the 3
Yeah.
because of float 3. Gotcha. Yep, after hitting the enter twice, notice that's the same answer we put right here. So 2 applications that we got right there. That's a cool way to put that into the calculator for TI-84s. Other questions or comments so far? Okay, well, we have 2 more equations at about 22 minutes. I'll leave it up to the class. We could solve this exponential one we were looking at. This one's pretty not too bad. It's kind of like what we did above. Or we could try to do this one, which is supposed to be a Halloween problem for a zombie outbreak, and we can find out when half of Idaho Falls is infected. This one's a lot harder. That's the downside. And if we decide to do this one, I would put the solution down here later. So class's choice. Sorry, say again. This one down here? Oh, yeah, it already happened. It's happening right now, I guess we could say. How about we try this one here and we can come back to the other one? Okay, actually, we probably won't have time for that, but I'll put the solution back on here when we upload it. So this one is the bonus question we'll go for. It's the application problem. It says the population of Idaho Falls is about 64,818 in year 2020. We'll use that value. And today, 7:43, a few minutes ago, a zombie infection occurred nearby at the intersection of Anderson and Holmes after a train that was transporting biological material overturned. You can imagine happening. That's a terrible trade. They can just park on that track for hours, so who knows what's going on. They say the initial size of the outbreak was 13 people. On-site personnel from CDC estimate that the zombie infection will spread according to this model, which is almost a logistic equation. Z of T is the number of zombie infections at T hours. And this is our equation. We want to know how long it's going to take for half the population of Idaho Falls, so 32,409, to become zombified. So that means we're really just solving this. Z of T equals 32,409 people, but that means we're solving this equation. Let's input the Z of T function on the left. It's 64,818 plus the natural log of T plus 1 divide by 1 plus 4,980 e to the power of negative 0.4 T is set equal to 32,409. Definitely a weird function. We'll have to ask the CDC folks of how they came up with that. But now for solving this equation, I have no clue how it would resolve that if there's a logarithm and an exponential, both involving the variable t. I don't have any tricks for getting t out of both of those functions at the same time. So instead, we want 0 on one side, but I wouldn't want to subtract that either, because then we'd have to differentiate this through quotient rule. That's a really bad time. So there's a lot of flexibility with Newton's rule. You can just take any equation that came from this in an algebraically sound way and use it on that equation. So the easiest way to do this is definitely clear your denominator first. You can take that full denominator and multiply it to the right-hand side. Visualize as a halfway cross product. Gives you 64,818 plus natural log T plus 1 equals, now 32,000 first multiplies this 1 here, so 32,409. Then when we multiply over here, imagine this as a group that we're distributing through. 32,000 multiplies the 4,980. Let's get that value in. 32,409 times 4,980 gives us this figure. It is, oh geez, I wish they printed commas. 161 million. I'm good with 6 digits, but 9 is quite a lot. 39, oh, did I get that right? 396,820. I think we've got it. 396. 820, e to the power of negative 0.4t. So this will be way easier for us to work with because now when we put 0 on one side, we'll have a function which, when we differentiate, it's not the quotient rule any longer. Much, much easier to get through. So I'll put my 0 on the right-hand side, and we can start with the natural log. It just looks nicer. Natural log, t plus 1. We're taking 32,000 minus 64,000, but that was the population of IF. That's half the population. So it's immediately just a plus 32,409 again. Then subtract this figure, minus 161,396,820 e to the power of negative 0.4t. Definitely messy, but applied problems get messy, unfortunately. That's an unfortunate fact about them sometimes. But this function on the far left, this is going to be our f of t function. I'll just indicate it this way. We now next need f prime at t. Let me just put that in green just to emphasize. That's our function there. The derivative of f at t, try to put an x in there. It must be really used to x's, goes like this. First, we differentiate the logarithm. We'll go 1 over t plus 1. Then we have to multiply it by the derivative of t plus 1 as per the chain rule. Well, that's just a times 1. And putting it here in the notes is just a way to say, oh, we caught the chain rule, but this is all that really happened. So we didn't miss anything. This constant is going to go to a 0, so we skip on over to this one. Now it's a constant multiple rule. That big constant negative 161 million stays alive. Then we differentiate this function. Derivative of the base e exponential is itself. Then we multiply it by the derivative of negative 0.4t, which is another negative 0.4. And that's our derivative right here. Ordinarily, I'd probably simplify it a little bit more, but honestly, if you're just going to plug this into Newton's formula, it's kind of okay just the way it is. So I'll leave it right in that expression and not trouble over unnecessary multiplications that is only increasing my odds of making a simple mistake. Instead, write xn equals, oh, I forgot one thing there. Our author likes to go xn plus 1 equals xn. Some books you might see an xn here, xn minus 1, but we go it this way as per our author. In this fraction, we're putting in f of x, which is this function here in green, so natural log t plus 1 plus 32,409 minus 161,396,820 times e to the power negative 0.4t. So that fills in our numerator. And for the denominator, it'll be this quantity. I'm going to write the fraction sideways. It'll look more similar to what's going in the calculator. 1 over t plus 1 for this part. I'll put in the constant. Well, we could simplify a bit if we wanted to. These two are going to combine to a positive value. So I'll write plus 0.4 multiplying this expression next. Here's the 161,396,820 e to the power of negative 0.4t. So that's finally the expression we're going to use. But the one thing I still don't know is what a good initial guess might be. We have two routes. We can either plot the function or just throw down something. This is in, let's see, z of t. This is measured in hours, it looks like. Or let me take another look at this. For some reason, I thought it was minutes for the unit. I might have a small issue here with that unit there. I think our time was in minutes, but let's take another look at our graph here. I'm going to put in f of t just to get a feel for where everything is. So our function f of t is very nasty this time, but that's okay. Newton's method doesn't care. We just have to have a non-zero derivative down there. So natural log t plus 1 plus 32,409 minus 161,396,820 e to a power of negative 0.4 t. So we've got our function in. And I need to recall, this is with a population of Idaho Falls. So the vertical axis is way, way up there. But already, this is a pretty decent initial guess, about 20 minutes. I think I do have a unit problem here. That's what's meant to be in minutes rather than in hours, like it was indicating. But let's try a guess of about 20 minutes, or 21.283 is just fine as well. I'll go with 20. So back to the problem. Let me fix this. This was supposed to be minutes. Let's guess 20 minutes. It was supposed to be fast, like a real zombie apocalypse. So lots of things happen really quickly. So initial guess of 20 minutes. Now we're just plugging everything into the calculator. Any questions or comments, folks, to this stage? Okay, so for a calculator, let me try to remember that trick that you were mentioning earlier, Summer. What we need is not the full equation. We just need up to right here where xn emerges. Let's clear all this out. Initial guess of 20 minutes. Now we're going to use the process in full. At second negative for the prior answer, minus, and if you have a fancy calculator, hit alpha y equals. And I believe it's option 1. Hey, learning occurred. I remembered that. Thanks. I'm probably going to forget it in a moment, but I'll come back to this video when I need that next. That's a really cool trick. Then this goes in. Let me make this a little bit bigger. Natural log t plus 1. I see what I did that. Anytime you see the variable, just use the prior answer. So second negative sign here, plus 1. Should be able to make that a little bit bigger now. Then 32,000. Oh, definitely close the parenthesis for your natural log first, then type in the next information. 32,409 minus 161,396,820. Oh, thanks for spotting that. I've got a times right there. That's going to definitely not work out at all. Thanks for spotting that. So second insert, if you do it just right, I might have the right spot here, plus. Okay, so we got the plus in. Any trick like that you could use the calculator is always a good idea, since retyping this stuff is just exposing us to more chances of simple mistakes. So now for base E, it's under the logarithm key, so hit second, natural logarithm, negative 0.4, a prior answer, so second negative, and that should be our full numerator. Down arrow takes us to denominator, and we'll just do that all over again. 1 over t plus 1 is how it starts. When I'm right up here. Oh, redo the fraction, gotcha. Let's try that out. So alpha y equals, enter. Yeah, that's really cool. 1 over t plus 1. Thanks for showing me that. I mean, I knew you could do it once, and then I forgot. I guess if you could do it once, you can do it a whole bunch of times. That's kind of cool. Then back over here, it's 0.4. And 161,396,820. Second, natural log key for the base E exponential, negative 0.4. Second answer, and that should be it. Yes. Let me scroll to the left. Oh, I missed it again. Thanks for spotting that. I'm having a hard time with pluses today. So there's supposed to be a plus here and another plus right here. Thanks for spotting that one. It's like the trick on insert is try to get it right over here where you overwrite it. Oh, I've got before, yeah, right here. Thanks for spotting that. Geez, this one's getting tough to get in. I appreciate the help, folks. So right here is where it should go. Second insert and a plus sign. I think we've got it now. Thanks for spotting that. So plus right up above and The one that I just corrected was right here to separate that plus. Okay, so back over here. Let's double check. I think the only thing I would do is close the parenthesis, but I think we're all set now. Does that look right to folks after those corrections? Okay, so our next value is 21 minutes. Enter again, and we have 21.267,768. We have a 7,678,678. I think we're just about getting stability on these last digits. It's interesting, this calculator takes a little bit longer to run the iterations through than the TID3. I'm not completely sure why that is. Oh, but I wasn't paying attention. I think we've got it, folks. So to 6 decimal places, this will be 21.282723. So our value, 21, and I definitely forgot those digits. Let me try again. 282,723. Minutes is amount of time for half the time of Vital Falls to become zombified. According to the model, of course, it's just a model. It's not guaranteed to be accurate. But we did it, folks. Again, this is a horrendous equation. And the moment you get a value out, never a bad idea to return to the technology. Just see how close we were. We're at 21.283. That's what this would have rounded to if we rounded this answer to 3 decimal places. So I feel like we're have the right value here. Well, any questions at all, folks, on the conclusion to this one? Okay, well, have a great night, folks. Stay safe during Halloween, and when we come back, we'll be in section 4.9 on Wednesday. Again, this is kind of a interesting fluff kind of section. It's one of the neater examples of the first derivative applications, but it's a bad one for exams. So think of this as purely more of a homework topic.